All right, this is problem 39 from chapter 10, and it is a relatively complicated problem. But like all of these problems, all of the individual parts, I think, are pretty simple. What makes this difficult is the bookkeeping, keeping track of all of the forces, making sure that you don't make any mistakes regarding a sign, and just keeping your work nice and neat. That's going to help things along. In this problem, we've got a 2 kilogram block. It's sitting on top of a surface, and yes, there's friction. That's described by a mu of 0.360. The 6 kilogram block is on an incline. It has the same coefficient of friction. And there's a pulley of mass 10 kilograms. It has a radius of 0.25 meters. The first thing that you're asked to do in this problem is to draw a free body diagram for mass 1, mass 2, and the pulley. And I've done that. Throughout this little explanation, I would encourage you to hit the pause button if you need to take a closer look or a longer look at some of these points. Well, the first thing that we're supposed to do after drawing the free body diagram is ultimately find the acceleration. This contraption is going to accelerate. That 6 kilogram block is going to slide down the incline. The pulley is going to spin, and that 2 kilogram block is going to get dragged along. Well, let's take this in parts. Let's look at the sum of the forces that are on block 1. And we, of course, should be familiar with this by now. You can identify the sum of the forces as mass 1 times the acceleration, which we don't know. We're trying to find that. But we have another way of describing the sum of the forces on block 1, and that's the tension 1. Subtract from that the force of friction. Refer to the free body diagram right above. And you can see that what I've done is I've expanded the force of friction. On that last line, it's mu times mass 1 times g. We can do the same thing for block 2. We look at the sum of the forces for 2. That's mass of 2 times the acceleration. And if we describe that yet another way, that's mass of 2 times g times the sine of 30 degrees minus tension 2, which we don't know. And we've got to subtract the force of friction there. That's mu times mass 2g cosine of 30 degrees. Just want to make sure you understand that m2g sine 30 degrees, that's the component of gravity parallel to the ramp. And you can see that's what I've indicated there in blue. That's the force of gravity parallel to the ramp. In red, that little bracket is the force of friction for object 2. Again, stop or pause the video if you need to look at this for a little bit longer. Well, we can't go any further regarding the forces and tensions and accelerations, so let's see what happens when we look at torque. Torque, we know, is I alpha. The I that we're talking about is the moment of inertia for the disk. That's the pulley. That's 1/2 mr squared. And rather than write alpha, the angular acceleration, I'll write that in another form, A over R. All of that reduces down to 1/2 big M R times A, the acceleration. And that's the acceleration for the whole contraption. The 2 kilogram block, the tangential acceleration of the pulley, and that 6 kilogram block as it slides down the incline. Well, we have yet another way of describing torque. Torque is, of course, going to be T2 minus, I'm sorry, that's not T2, that's torque 2, tau 2 minus tau 1. And we can expand that out. That's what you see with T2R minus T1R. Again, we keep everything headed in that positive direction. Well, I've gone through this next step rather quickly. We've set those two ways of expressing torque equal to each other, and we've simplified. And then you may wonder, well, what's with that next line? Well, the next line, all I've done is if you draw back up to where we have m1a equals t1 minus mu m1g, I've solved for t1. and likewise for T2. You notice that when we were solving for torque, I had 1/2 that big M A equals T2 minus T1. Well, let's find T2 minus T1 given the way we have of expressing T2, T1. And you can see it leads to an ugly mess. As long as you're good with your bookkeeping, there's no problem. It's just simple algebra. Well, we can now describe 1/2 big M A is equal to, and instead of writing T2 minus T1, I'm going to write that expanded form. We've expanded T2 minus T1 into that term that you see, M2G sine 30 degrees minus M2A minus mu M2G cosine 30 degrees minus M1A minus mu M1G. And what I've done is I've grouped on one side of the equation all of the A's, on the other side all of the G's. Again, stop the video if you need to take a look at that. And now I'm just plugging and chugging. We're trying to solve for A, so let's factor that out. Then we know everything else. We know big M, we know M2, we know M1. We of course know G and we know mu. And we end up with an acceleration of 0.3085 meters per second squared. And then you're also asked to solve for T1. What is the tension in 1 and what is tension 2? We can go right back up to where we had already solved for that. We had said that T1 is equal to M1A plus mu times M1G. Just plug and chug and you get 7.67 newtons. And for T2, 9.22 newtons. And if you want to, you can check the answer in the back of the book, and we should have the same thing.